Okay, thank you. All right, so before I start my talk, I can see only video participants, so I won't see any chats, questions, so don't hesitate to turn on your video and audio and ask questions during the talk, because chat won't work. Okay, so the talk today is going to be a little bit different than other talks in this seminar. So usually we invite people to share their successes. And today I'm going to share with you some failures. But these are nice failures, I believe. And there are some nice mathematics that we can all learn from this. So this is about a project that started on a Homonolo meeting. It's a meeting organized by Prague, and there during this meeting 2 years ago, I believe, Milan Hladik asked a question about solving linear equations where those equations are allowed to have some errors. And then after Homonolo, we've exchanged some emails and tried to pin down this problem. And later, Honza Kratofil also joined in this small project. And we've been making some nice progress, and we are quite happy about what was happening. And we found some nice combinatorial nature of this problem. And we were a little bit sloppy about finding references, and we kind of missed a very nice generalization of this problem. And it turned out recently we've discovered that this nice generalization has already a nice solution that kind of kills all our results. So I will tell you about this problem more, and I will show you this solution. Perhaps there are some nice things left to do. So in the end of the talk, I'll try to well, maybe this project is not finished after all. So one more thing, there's a manuscript that we've been writing, and I've been sharing this manuscript with some of you. So I would kindly request you deleting that manuscript. So yeah, we didn't attribute the results correctly, so it's better that this manuscript is no longer in, nobody reads it. All right. So this is the status of the problem, and I hope there is some future. So so yeah, this is the state of the project. In particular, there was we wanted to use this problem on some programming competitions. So I guess we should reconsider that after this talk. Okay.
We didn't use this problem.
Yes, we didn't use this problem, but yeah, we should talk about it later. Okay, so the original motivation for this project was the following question. We have some system of equations, and we ask, can we solve them? And then we want to allow some error in the system matrix. So we can just write that some of the entries are a little bit unknown, and there is some error allowed there. And what would it mean to solve such a system? So basically, you can consider either solving it for every possible choice of the value for this 5 plus epsilon, or you can solve it for some value. All right, and both of these problems are interesting. One of them is maybe harder and even of more importance, but I will be interested in this notion where I want to find one particular matrix that satisfies those constraints and allows for solutions. So I want to find some value, for example, 2.5 here and 5.01 here, such that this matrix that we get is non-singular, and we can use like standard methods. And so this was the notion that we were working with, and and we soon realized that, well, those real values do not really matter. Equivalently, we can ask ourselves, when given a matrix over some field, can we fill the blanks to avoid singularity? So there are two places in this matrix that are not yet decided, and we want to fill them and have the matrix non-singular. Okay, and there are some examples that I want to start with, and in the first example, let's say that the field is it's just a two-element field, and all of the values are 0, and we have those blanks on the diagonal. And in this example, if we choose 1 for each 3 entry, we get a non-singular matrix, but any other choice is bad, because then we get a 0 row or 0 column, and we get a singularity. So in this example, we can have a singular matrix, we can have a non-singular matrix, and there's only one way to get a non-singular solution. So we can call such a matrix weakly singular. So there is a way to make it singular. But in the other example, whatever we do for those 3 entries, we will always get this 0 row, and this matrix will always be singular no matter what we do, and those matrices will call strongly singular. And I'm interested in deciding if a matrix is strongly singular. So I want to decide whether a matrix can be completed to be non-singular. Okay, so I hope the problem is easy enough and do not require any more introduction. So let's make some easy observations. So the first observation is that, well, if we are interested in singularity, we have this tool which is called determinant, and it's a polynomial, and it's zero when a matrix is singular and non-zero if it is not. And we can write this use this determinant polynomial where we have three variables for unknown entries, and those fixed entries are just plugged into the determinant. And this polynomial has some nice features. The first one is, well, the resulting polynomial is a polynomial in some variables, and each of these variables corresponds to one of the three entries in the matrix. So the degree of that polynomial is at most n, because this polynomial is a sum of monomials of degree n at most. So this is one nice feature. The second one is that the degree in each variable is at most 1, because in each monomial we have each variable appearing at just once. It's just one entry in the matrix, so it's a very low degree polynomial. And these observations allow us to conclude that well, sets are irrelevant. So it doesn't matter what are the sets that we are choosing the value from, because if this polynomial is non-zero, so it can be greater than 0, and then we have a non-singular choice of the values for three entries, and then the degree in each variable is at most 1. So this means that if we have a solution that makes our matrix non-singular, then we can take any of the three variables and change it to almost any other value, except possibly one that is a wrong one. Okay, so this allows for perturbation of the solution, and this allows for working with field extensions. Okay, so or maybe first, like maybe first observation is, if I allow any two values for each free entry, it's the same as allowing all the values in the field, because we can find a solution that uses any values, and then one by one, by substituting one of those two values for each free entry, we can repair that solution so that it chooses the value for each entry from the set of size 2. So now we can make a one step more. So we can if we are working with a finite field, we can work in some extension of that and have many more choices for each free entry. And let me go back to this this example. In this two-element field, it seems that it may be quite difficult to find the correct solution because there is only one. So what we can do, we can work in much greater field, that is a finite extension of two-element field, and then have many values for each entry. Okay, so I've had two, but now I choose some bigger sets here for the diagonal. And now if I randomly choose values, I have quite good chance that I'm not seeing any zero, and then I get a non-singular solution. So extending field allows us for more freedom. And then when I get solution which uses those strange values from the field extension, I can one by one repair them and get solution in 0 and 1. Okay, is that argument clear? Okay. So this is this was the first observation, and this so this view in terms of determinant polynomial allows stipulates a generalization in which the choices for the undecided entries in the matrix are somehow dependent. So in our original problem, it was not so. Each choice was independent, but maybe we can some of the ideas generalize well to the setting where the choices are dependent. So we can have some, for example, linear functions in the matrix and have a different set of variables that we want to set so that the resulting polynomial is non-zero. Or maybe we can even substitute some polynomials into this matrix, and some of the ideas still work. And later it will be important to understand which of the ideas work for this original problem where the entries are independent, and which work also for the generalization. Okay, so the next observation is that we can apply combinatorial Neutralization to the determinant polynomial, and basically I hope most of you have seen combinatorial Neutralization. If not, then I won't be able to introduce it properly, but basically it's not that important. The rest of the talk will not depend on it very much. So basically combinatorial Neutralization tells you that if the polynomial has some monomial with non-zero coefficient, and this monomial looks like this, then you can argue that P is non-zero on every cube of this size. So if you have enough choices for each of the variables, then you will get a non-zero value of the polynomial. It's so this is connected to our problem in many ways, but maybe the most important is that it's the same thing as if you look at the determinant polynomial and just compute the polynomial explicitly and evaluate this polynomial on every possible choice, it's the same thing. So if the polynomial is non-zero, so it has some terms, then it has a non-zero value, provided the field is big enough. So we need to have the field of size at least one more than the degrees of the variables. So in our original problem, the variables had degree 1. So combinatorial neutralization gives us solution in every field of size at least 2. But if we consider those generalizations, it's important to consider them on fields big enough, meaning at least one more element than the degrees in the polynomial. Because for smaller fields, very bad things happen. So you can have a determinant polynomial that is non-zero, but it's always 0 when you evaluate it, and basically the term determinant and determinant are different notions, and there's a sharp threshold in the complexity, meaning for fields that are basically of size d, those problems of completions are NP complete. So so basically, we don't want to go there today, and maybe never. Okay, so so the next observation is that this polynomial formulation brings us naturally to polynomial identity testing. And what it means, there's a very easy Monte Carlo algorithm. So basically, we can use Schwarz-Zippel if the polynomial is non-zero. So it can be we can find values for the polynomial to get a non-zero value, and the field is big enough, then we have a fair chance that a random assignment of the values will give us a non-zero value of the polynomial. So so basically, this brings us again to this first example. If we are interested in completions over Z2, we should choose a some field extension that is big enough, linear in the and then just make a random assignment and and this gives us a Monte Carlo algorithm. Okay. So all right, so I couldn't resist myself because this is another topic that I've been advertising lately. So if you know Alon-Furedi result about counting the non-zero values of polynomials on cubes, then it's a nice thing that this Alon-Furedi result can be applied to this setting and gives better bounds than Schwarz-Zippel. And just as a side note, I'm again advertising this Alon-Furedi result, which gives better, even sharp, estimates on this probability, because you can get better results than from Schwarz-Zippel. Okay, so we have an easy randomized algorithm that decides strong singularity, and now we want to work with this more. And the next step is to generalize this a little bit more. So instead of singularity, it's more convenient to consider ranks. So I will say that so what is a rank? So you can define it in many ways. But let's stick to this definition, where rank is the maximum size of non-singular submatrix. And in our regime, where the fields are big enough, well, term rank and rank are the same, because we can just find this submatrix that maximizes the well, but that realizes this this rank, and for that matrix the permanent the term determinant and determinant is the same. So basically, for fields big enough, we can either find a substitution of the three variables that maximizes the non-single submatrix, or we can look at the polynomials, the determinants of some submatrices, and it's the same. So so from now on, we will be interested in this Sudoku problem, where we want to maximize the rank, and if this rank is equals the size of the matrix, then we get a non-singular assignment. So so it's a generalization of our problem. Okay, so and now the next observation is that maybe it's a good idea to see how Gaussian elimination works. So basically, we can take our matrix with those three variables and try to do Gaussian elimination. And we have to do it in the field generated by the scalars and the three variables. And then this this is slow because what we get is that you can look at it as a you can view it as what's the name? Okay, so during the elimination, you will get values that need long descriptions, right? Because you you basically have their fractions of polynomials in those three variables and over k. So so during this elimination program, you will have very long entries in your matrix, and you're not going to make it in polynomial time. But again, you can make a random choice of values for the three entries in your matrix, and look at the Gaussian elimination working in K, and just look how it behaves, which rows and which columns it uses to reduce. And for similar reasons, you can hope that this the way this Gaussian elimination on random choice of values works is the same as it would work on terms, right? So you can somehow simulate Gaussian elimination with high probability. Because during one Gaussian elimination, you just calculate rank for some submatrices and not too many, because it's a polynomial time algorithm. So if field is big enough, then you have fair chance that all the ranks are okay, and this is a good simulation of this Gaussian elimination on terms. Okay, so so these were some easy observations on the problem, and now we can move to better solutions. So the first thing that we need to do is some duality. So basically, the duality is that if you want to get maximum rank, then what you can do is you can find a cover of three entries, meaning you can take a set of rows and columns so that they cover all the three entries. All right, so let's draw something. So this is my matrix, and there are some three entries there. Okay, let's say. Okay, so so now I will choose some rows and columns and erase them, and what is left has no more three variables, so I can compute the rank of this resulting matrix, and then one can show that there is a cover such that the maximum rank of your matrix is just rank of this matrix without free entries, plus 1 for each deleted row and each deleted column. All right. So basically, what it means is that there is if the rank is low, then there is some matrix there that has no free variables, and then you add remaining rows, remaining columns and remaining rows. Some of them have some free entries, but at each point you get +1, right? So there was some rank here, and for each added row, the rank each added column, the rank increases, and for each added row, also the rank increases. So this is the duality in this problem, and it strongly resembles the maximum matching equals minimum vertex cover in bipartite graphs, and it's really so. So if we have a bipartite graph and we represent it by a matrix in which for each x and y, so this is vertex in one of the bipartite sets and this is in the other, if they are connected by an edge, we put a free variable there, and if A and B are not connected, we put 0 here. Okay, so now basically in this particular matrix, this duality is the same as Koenig's min-max for matchings in bipartite graphs. And the funny thing is that well, but basically this was our first problem that we were working on, and in terms of those interval matrices and solving linear equations, we were hoping to find such a duality, so characterize the strongly singular interval matrices in this way. And after we did it, we found this this result, which did the same, but we didn't find this one, and this was unlucky because other authors cited this result, and we didn't find a branch of the research that we should have found. Okay, so how do you prove this this duality? So we can make inductive proof on the number of free variables. And basically we can fix variables one by one, and on the way it's enough to maximize the rank of every fixed submatrix. Okay, so what I mean is that after, well, there is some free variable here that we want to fix, and what we can do, we can consider any submatrix here for any set of rows and columns, and consider those submatrices for which this is the last free variable. Okay, and now we can show that there is a choice for the value, so that the rank of every such submatrix is also maximized. And maybe it's nice to do it properly, because it will help later. So say that there is some matrix, and this is this last free variable. Okay, so first we look at this submatrix, and we can say that rank of this one is Q. Okay, and because we didn't make a mistake earlier, we know that this is the maximum possible rank of this submatrix. And what are the possible ranks for the whole submatrix? And it's either Q plus 1 or Q plus 2. And there are a few cases, but it's important to see what are the possible ranks for this submatrix and this submatrix. So I will well, there are some possibilities. Let's start with a simple one. So say that this one is Q and this one is also Q. So basically what it means that adding this column to the matrix that does not increase rank, and adding the first row also does not. But now we add this one missing entry to the matrix, and basically there is only one bad choice for the value, right? Because we can consider this Gaussian elimination and run it in the whole matrix, and what it will do, it will result in Q ones here, but this Gaussian elimination will zero all the values here, and zero all the values here, and here what will happen, we will have some term here that is still dependent on the variable in that entry. So basically what it means that this there's only one bad choice for this variable that zeroes that entry during this Gauss elimination. So any other choice of the variable will be better, and basically this this gives us rank q plus 1, and there is one bad choice. Okay, so there are some other possibilities. The first one is all right. So what happens if we have such a situation? Basically, no matter what we do, we will get q plus 1, right? Because this part has rank q, and adding one row can only increase rank by 1. And this was already achieved in this submatrix. So whatever we do, we get q plus 1. And the last interesting thing is q plus 1, q plus 1. And in this situation, it's also not important what we choose. Whatever we do, we will get q plus 2, right? Because basically whatever we get q plus 1 here, and the rank increases by 1 whatever we do in this cell. So we get q plus 2 whatever we do. So basically there was only one bad choice in one particular situation. And to finish the proof, basically we only need to notice that there are finitely many submatrices. Each of them kills only one choice. So if the field is big enough or infinite, because why not, then there is a choice for the value such that we get maximum rank in every fixed submatrix. Okay. So this is the duality. And this duality allows for Las Vegas kind of algorithm, because there is an easy certificate that maximum rank is at least q. You can just bring some choices and compute rank and just see that it's at least q. But this duality gives us easy certificates for max rank at most q. So I can just pinpoint some submatrix of low rank and say, well, this is a submatrix of low rank, and for every other row and other column, you are allowed to add one more, but still you're not getting to q. And this is an easy certificate because, well, you can verify it, and it's only a choice of rows and columns. And going back through this proof, basically you can you can construct an algorithm which gives you either a randomized algorithm which gives you one of those certificates. So either you get a certificate that max rank is at least Q or at most Q, and this allows for Las Vegas algorithm because you can run this randomized algorithm that gives you positive certificates and negative certificates, and at some point with high probability you will get matching certificates. So you will get both choice of the values for free entries and this submatrix of low rank that prove both inequalities, and you get a Las Vegas algorithm for maximum rank. And we were playing with this Las Vegas algorithm, trying to make it more robust. So trying to make it work for those more general problems where we allow for linearly dependent entries. And without much success, but I believe it's an interesting question whether you can use this Las Vegas algorithms in some more general scenarios. Okay, so I have some time left, so I would like to present the polynomial time algorithm for matrix completion. So it's an algorithm that is all right. So there are a few algorithms, and I will show the algorithm by Gaussian from 1999, and there is an earlier algorithm from 1903 by Murata. It's and it's a funny thing. So this other algorithm is described in a different setting a little bit, and then it uses matroids, and it's less explicit and less combinatorial. So I prefer to present this Gaussian algorithm, which is a nice combinatorial algorithm that kind of exploits this duality, and it resembles some bipartite matching algorithms. And I believe this Murata algorithm is also based on the same ideas, but less explicit and more difficult to present. And there have been some improvements. So basically, Berdan took Gaussian algorithm and tried to speed it up, but basically working with the same ideas. So in the original paper, this polynomial algorithm by Gaussian runs in n to the power 9, and this, I believe, is n to the 4th. And there have been some work on this Murata approach, and this set of authors in two papers were able to speed this approach to basically n log n, and this is n to the fourth. So so the bad news is that this matroid approach is faster than a nice combinatorial algorithm. So maybe it's an interesting point to try to look closer on this combinatorial algorithm that I'm going to present, and try to speed it up to match, or even to match this matroid approach. Okay, so what are the ideas behind the algorithm? Basically, these are ideas from Edmonds and Dulmaga and Mendelssohn on matchings. So we'll try to augment matching algorithms so that they work with rows, columns, and ranks. And before I describe the algorithm, I need to define some decomposition of the matrix. So I will divide rows and columns into 3 sets. So first we have set D, and these are rows and columns such that when you remove them, you do not change rank of the matrix. So whenever you remove one row or one column, the rank either stays the same or drops by decreases by 1. So I want to have those D rows and columns such that they don't change rank. Okay, so this is easy, and this D stands for dependent, right? So if a row or column is dependent, then basically you can remove it and the rank stays the same. Okay, so the second set is such that if you remove row or column in set A, then the set D does not change. All right, so so this is a little bit more tricky. Basically, those A rows and columns are not dependent, but if you remove them, those things that were dependent are still dependent. Okay, and there is the third part, which is simply the rest. Okay, and now we can state the algorithm. So the algorithm works as follows. You basically choose any values for the 3 variables, and we want to describe the algorithm in terms of perturbing the values. So the algorithm would be to perturb some variable, some free variable, meaning change the value of that variable so that we can increase rank. And and this is the well, this is a greedy algorithm that tries to increase rank, and this greedy algorithm does not work. So there are examples of matrices such that whenever you try to change value of one of the three variables, the rank stays the same, but still this is not the maximum possible rank. So the observation by Galini is that you can change this to a slightly different idea. So you have some choice of the values for three variables, and now you want to find one of those so that either increase rank or you have more dependent rows and columns. Okay, and for this algorithm, you can prove that when this algorithm cannot make one more step, then you have a maximum rank. So so this is the idea. So it's again a greedy algorithm, and and I want to sketch the ideas that allow for the proof that this approach works. So so let's let's draw something. So we can. So this is our this is our matrix, and we have those D rows, D columns, A rows, A columns, and C rows, C columns. Okay, and so basically, I'm going to make it a little bit messy, but maybe it's the best way. So you can either look at a particular realization in which you have substituted values, or you can look at this matrix with three variables, and basically those you can define those sets DAC for both structures, and these are different things. For particular realization, the rank can be lower and the set of dependence lines can be lower. So maybe let's fix some realization now, and we can define those dependent lines for a particular choice of the values for free variables. So this is just a matrix with entries from the field. And because those dependent lines are defined by dropping rank, then basically for a random choice, it doesn't really matter. You get the same things. But I hope we won't mix it too much. Okay, so so this is the composition of our matrix, and the first observation is that that those A rows columns are not important. So it can happen that you have them in your matrix, but if you do, if you remove one of them, the decomposition does not change. So the D columns and D rows are the same. So A rows and A columns are the same. So you can just remove them one by one, and basically they do not matter, because then when you introduce them back, each of them increases rank by one. So they are easy and not really important. So you are left with those D and C uh, uh, D and C rows and columns. So all right. So now let's find some place in this matrix that corresponds to a free variable. And let's see what happens when I perturb it. So, well, for this particular choice of x, this is the composition. So what happens if I change the value at this entry to some other? So I can do something bad and drop rank of the matrix. Okay, so this is first to the decrease. All right, so it can happen that assigning other value will decrease rank. And again, it's the same argument as before. There's only one such value. Okay. So what other bad things can happen? I can remove something from D. Okay, so there was some column or row that was dependent, and after changing the value at that point, it's no longer dependent. And this requires some little work, but basically, again, for each row and for each column, there's only one value that can destroy this dependency that was there. So in the end, there are at most that many bad perturbations that kind of make step backwards in our algorithm, and every other choice can either leave us at the same rank and at the same set of Ds, or it can move us forward, meaning that either rank increases or the set of dependent rows and columns increases. Okay, so perturbations are not that bad. So the last thing is, what does it mean then that there is a free variable in this D row and D column? So this is something very impossible. All right, because so this is a dependent column and dependent row, meaning that if we delete them, the rank stays the same. All right, but when we introduce them back, we have this free entry, and we can, as before, increase the rank by choosing value for x. So basically, this is impossible. There are no, or rather, I shouldn't say it's impossible. If there is a free variable in DD, we can, by choosing other value for this free variable, we simply increase rank. So we make a step forward. Okay. And the last thing is we need to do something about free variables that are here. So in D row and C column. And it's a little bit more complicated. But basically what it means is that if we have a free variable that is in a dependent dependent row and non-dependent column, we need to use that after removing this column C, the set of dependent lines changes, right? Because it was not in A. And basically this this change can be used to show that changing value in this point can bring that line that changes to D in just by changing this value. But it is again a simple argument of the same kind. You simply fix some submatrix and you have choice at this point, and this choice increases some rank, and basically it's again the same idea. So this is all, and basically after that you can see that, well, maybe let's draw it again from the beginning. You have this composition, and you know that this part is fixed, and this part is fixed because when the algorithm stops, so you can't increase either rank or the set of dependent lines in one substitution, in one perturbation. We know that these two parts there are no free variables here. Well, you can also say the same about this one, but it won't be important. And basically what happens is it's the same duality here. So you just compute rank in this part. So you just compute rank of this submatrix, and you can then argue that the rest is well we can see that the other rows and columns is cover of the free entries in the matrix, and it's the same thing as before. We use this duality to finish the proof that this maximum rank and equals the minimum cover plus rank of the rest. Okay, so this is the polynomial algorithm. Basically, you can how many steps you can make. So in each step, you either increase the size of D or increase rank, and you can increase rank at most n times, and on a single rank you can make n squared steps, increasing the set of dependent lines. So after n to the third steps, perturbations, you will the algorithm will finish. And each perturbation, you need to check at most 2n plus 2 possibilities of other values. So this is one more in the exponent, and then you need to do rank calculation in the matrix. So you can do it in n to the third. So if you all right. Anyway, so Galen was not interested in optimizing it, and it's a polynomial algorithm, anyways. So basically, if you are more careful and do something about in a correct order, then you can make it faster, but not fast enough, I believe. Okay, so this is the state of this project. These are the things that I know, and there are still a few questions that I find intriguing. So the first one is to improve this complexity and make it better. So maybe maybe it's possible to improve this complexity below n to the third. The other problems concern those linear matrices where we want to allow the entries of the matrix to be some linear functions of the variables, and it's a very nice problem, and it might be a difficult one because those like the randomization of this polynomial identity testing for permanence seems to be an important question for circuit complexity, and maybe it's innocently looking a difficult problem, but I still hope for a Las Vegas kind of algorithm. So maybe if I'm not able to de-randomize it, I can still hope for negative certificates, and maybe those negative certificates can be used to devise the Las Vegas kind randomized algorithm. And there are some special cases of matrices with some other constraints which appear in the literature, and I don't want to go into much detail, but these are interesting. They have some applications, and for that reason, there is some interest in linear matrices that satisfy some additional conditions. And the last thing that that I believe is of some might be interesting is to give better bounds for those probabilities that that some ranks are bad. I've mentioned that this Allen-Furedi allows for some better bounds than Schwarz-Zippel, and possibly we can use it to have better bounds on other on other probabilities, like for a random choice of values. I would like to not only the maximum rank of the matrix to be realized, but I want to the maximum rank to be realized for every submatrix. And if that would be possible, then maybe some things would be simpler. Okay, so so this is where I would like to finish, and thank you.
So